Hello, I'm Hugh Manfield, and welcome to the Fluid Space Theory Lectures. Today, I'm going to reveal the secret of dark matter based on fluid space theory. And if you want to find it in print, with all the math and derivations listed in the appendices, you can pick up a copy of my book, and you can also enjoy a nice science fiction story in the first half of the book. So in the last video, I explained how we see the orbits of stars going around galaxies faster than predicted by Newton. Newton would predict this dotted curve, while we actually observe this higher curve, stars orbiting at a higher rate. And if you subtract the predicted Newton curve from the observed curve, you get this orange contribution of dark matter. And it's interesting that dark matter always contributes in this sort of form. Physicists have been looking for dark matter for a long time, and so far they've never found it. And the reason they haven't found it is because they're looking for a particle. Dark matter is a field, not a particle. If you think back to my earlier lectures, where we looked at fluid space theory as fluid flowing down a funnel into a gravitating body. As it flows faster and faster, it becomes length contracted and time dilated, so that it begins to distort the space that it's in. And if we took that space out and let it expand back to its full length, it has changed the shape of the funnel to a hyperbolic shape rather than a straight cone. And what this means, I've taken a cross-section of the cone, where the blue funnel is the hyperbolic funnel that's actually the shape of the flow field, and the yellow triangle is the cone, the straight-sided cone that we imagine to be there when we look at the space around the gravitating body. Now, the blue part is length contracted and time dilated so that it fits within the yellow cone. Both of these spaces fit together. So the yellow is what you would see from outside the flow field, and the blue is what you would see from inside the flow field. So as this blue cone is length contracted and compressed so that it fits within the yellow field, a point on the side of the funnel will move until it lines up with a point on the side of the yellow cone. And what that leaves is the shaded area, which will represent the amount of contraction at that point in the cone. And this is a constantly changing value. And you can also think of it in terms of the unit cubes falling into a black hole. They start out 1 meter on each side, and as they fall inward, they become length contracted and time dilated so that they're losing volume. At least we observe smaller and smaller volumes as they fall into the black hole. And to put a number on that, we can take the proper volume, which is the starting resting volume of the cube, and we take the length contracted observed volume, subtract that from the proper volume, and we get the lost volume. And this is going to be a measure of the curvature of space-time. The larger the lost volume, the more highly curved space-time is. But space-time doesn't like to be curved. It's not like an iron bar that you can curve and then let go and it's going to stay curved. You relax space-time, it's going to flatten back out. It doesn't like to be curved. So it's like this water column. We see a laminar flow nozzle, and the column is continuously being bent by gravity. If we turned off gravity, the water stream is going to straighten out and go at a constant velocity in a straight line. And as soon as we apply an acceleration, it's going to fall back into the curve. So the curvature of space is an ongoing process. It's not just a one-time thing or a static situation. It's a flow. So when we look at these cubes falling in to the black hole, it's not just that the cube is becoming length contracted and time dilated. It's cubes per second. It's a flow rate. So you take the proper flow rate minus the observed flow rate, and you get the lost volume rate, and that's the contraction rate. To put this into equations, I took the flow rate, which is the area of a sphere, times escape velocity, and that will be the amount of space flowing into the sphere at any radius. Then we apply a Lorentz transformation to get the observed volume rate, what a cube would be if it was traveling at escape velocity. And we put that into the Lorentz transformation. And then we end up with this equation. And then one last step, we apply another Lorentz transformation to account for time dilation of the flow field. And this is the equation that we end up with, and when we plot that by radius and flow rate, we get this nice parabolic curve that increases with distance. And when I first plotted this, I thought something was wrong, and I had to check all the numbers, and I verified that this is actually the shape of that function, and it has the same shape as the dark matter contribution to galaxy orbital velocities. So to use this information, I had to come up with what I call the drift velocity. And that's basically the contraction rate divided by the area of the sphere at the level where you want to find out what the drift velocity is. So it's the same function, but now it looks a lot more like a gravity field. In this chart, I've plotted the acceleration field, which is relativity corrected Newtonian gravity, and I put the contraction field in there with it. And this is kind of like trying to show an elephant and a flea in the same picture. The acceleration field is way bigger than the contraction field, so it goes way off the chart. But there are different ordered curves, and the acceleration field is going to drop off faster than the contraction field. So way out at some long radius, the contraction field will cross over above the acceleration field contribution to an orbital velocity. And I use Newton's method to apply a scale factor, as I described before, to the acceleration of gravity. And the scale factor is equal to the contribution by gravity, the distance something will fall by gravity, plus the distance it will be contracted over the distance it will fall by gravity. And this gives me a number of 1 or larger. And then I plotted those scale factors based on the masses of several different objects and a radius, in this case, of 0 up to 20 AU. And 20 represents just about the orbit of Uranus. So when I started plotting these, I discovered something very interesting about the relationship between the contraction field and the gravity field. The crossing point is dependent on the mass of the object. The larger the mass of the object, the sooner that crossing happens. It comes inward. So as objects get heavier, going from planets to stars to bigger stars to black hole, the crossing point moves closer and closer, and the scale factor rises. So if we look at objects like Jupiter or the Earth or anything smaller, dust, asteroids, comets, they don't project an extra gravity halo. The contraction field is not effective really at all. The distance before it becomes effective is so great that the gravity has tapered out to almost nothing. You have to get to something the size of a sun before you start to see some small amount of the contraction field starting to take effect. And then I have 5, 10, 15, and 20 solar masses. So at 20 solar masses, you get a scale factor of 2 out at about 19 AU. And the scale factor of 2 means that the contraction field is contributing equally with gravity. So something may orbit maybe about 40% faster around a star with 20 solar masses. So let's look at bigger stars. This chart is for stars from 10 to 100 solar masses. So we have 10, 20, once again we're out at 90 for a scale factor of 2. And we can see that the For a 100 solar mass star, we get a scale factor of 3, which means that the contraction field is contributing twice of normal gravity, out at about 15 AU. And now I wanted to look at the longer range effects. And you notice these curves appear about the same. When you back out on the curve, it still has the same form. It's a rising parabola. So now I have stars of 10 to 100 solar masses, but now we're looking out at the radius in parsecs. So out at 20 parsecs, a 100 solar mass star could have 1,000 times more contribution from the contraction field than from ordinary gravity. Now, 20 parsecs is about 60 light years, so at that point, even a 100 solar mass star is going to have almost zero gravitational effect. So 1,000 times 0 is still pretty much 0. It's not until you get into the really massive objects that you see the projection of a strong extra gravity halo. Here I have bodies from 10 solar masses to 1,000,000 solar masses. So you can see that down here, out at 20 parsecs, even a 1,000 solar mass star or black hole will project a very weak extra gravity halo. You don't get a strong halo until you're up into the millions of solar masses, like the supermassive black holes at the core of most galaxies. So what this means is that the extra gravity halo, or the dark matter signature, is going to come primarily from the supermassive black holes at the core of the galaxy. Now, there could be a lot of very large stars by the thousands or tens of thousands or even millions within the galactic core, and those are going to contribute weakly, but combined they could add quite a bit to the extra gravity halo. So galactic cores are going to be where the dark matter or the extra gravity halo is projected from. So this is a bullet cluster, and it's kind of a test for theories on dark matter. What we see is there were two clusters of galaxies, and one shot through the other like a bullet. One is smaller and the other is larger. And what happened is that the galaxies and the stars and the galactic cores all passed through without interacting. They didn't touch. There's so much space between stars that can happen. But what did interact were the gas and dust clouds. And the gas and dust clouds are shown in pink, and they were pulled away from the galactic cores. And what's shown in blue is the residual dark matter or extra gravity halo that was left behind. So as predicted by fluid space theory, the extra gravity halos remained attached to the galactic cores. So fluid space theory passes the bullet cluster test. Another type of galaxy is a super diffuse or an ultra diffuse galaxy. And what they are small dwarf galaxies that were puffed up by supernova activity. And they tend to show either all dark matter or no dark matter. There's very few stars, but the stars that do orbit in these galaxies either follow the dark matter contribution line almost exactly, or they follow Newton's laws. So what fluid space theory tells us about this is that if there's a supermassive black hole at the heart of this dwarf galaxy, then it will be of the pure dark matter type. And if there is no black hole or a very small one, then it's going to obey according to Newton's laws. So fluid space theory passes the diffuse galaxy test. And I want to point out one last time how precisely the shape of the gravitational scale factor matches the shape of the dark matter contribution. This is no coincidence. It's a mathematical prediction of fluid space theory. It predicts that exact contribution shape. So there it is. Dark matter is a contraction field, and it's relativity at work. You can print the headline today because we know what dark matter is. At least you and I know what it is. Getting the word out is the point of these videos. So if you have a loved one or a friend who's working on a dark matter detector, please send them a link to this video, because they could actually be doing something productive with their lives rather than looking for something that doesn't exist. Now, there are some more things that fluid space theory predicts about dark matter and other topics, and these will be topics of future lectures. Why dark matter halos are spherical, the birth of early supermassive black holes, the arrow of time, the antimatter imbalance, and dark energy. So please join me. Until next time, I'm Hugh Manfield.